Hello, hello! Welcome to our unit on probability. I enjoy this unit to a point because there's a lot of real-world stuff here. Some people think of probability and they think of gambling. Actually, that's just one small application for probability. So much of modern mathematics relies on probability principles. If you start looking around, you're going to see probability. So this will hopefully give you a good little overview of basics of probability so that if you're reading the newspaper and see something about odds or chances, you'll be able to understand what they're saying. If there's somebody says something in the news or just you're out and about, you overhear something about probability, or even if you do participate in games like the lottery or horse racing bets or whatever, you'll better understand what these numbers mean. So that's kind of exciting about this chapter is there is a lot of real-world applications. We're going to start out just looking at the definitions and some small problems with empirical and theoretical probabilities, and then we'll go from there, and later we'll talk about odds and some other stuff too, combinations, permutations. And as we go along, as you do the homework, you're going to realize just how many ways probability comes up. One small non-gambling example, the weather. Today, I woke up this morning, I'm like, I want to go swimming for my exercise. I'm trying to get in shape, try to change it up, don't want to go to the gym every day. But it's been raining here a lot, so I looked outside and it looked pretty sunny, which gave me some hope. I was like, well, will it still be sunny, later when after I take my son to school? And I went online and looked at the Weather Channel, and sure enough, they said it was sunny, and then they said that thunderstorms should set in around 1 o'clock this afternoon. And they gave some percentages of percent chance of those thunderstorms hitting. And that percent chance is a probability. It's literally sitting there going, this is, it was probably something like 70 or 80% chance of me getting rain this afternoon around 1 o'clock. And what that means is that in the past, for all the times they've been recording weather, 70% of the days with those conditions had the thunderstorms, had the rain. The other 30% did not. So you can take that and go, well, if 70% of those days with these conditions had it, it's very highly likely that I will get it too. But it's not 100%, so there's no guarantee that I will get it. It could skip me. And sometimes that happens here. I live along the interstate, which is on a ridge, and often the storms will stay on the other side of that ridge. It's just something that weather patterns sometimes do with certain land masses. And so that 70% or 80% chance of rain might end up being, zero rain for me, just a few feet away. So unless it's 100%, not guaranteed. And you're not going to see it over 100%. And you'll never see it under 0% either. You won't see negative probability, and you won't see probability over 100%. It just has to be from 0 to 100 somewhere. We'll talk about that some more later. Alright, so what is this? Probability is everywhere. So when you encounter the chance of something happening, just like I was just talking about, winning games, getting caught in the rain, you've got these percent chances. That's probability. If it's been around for a long time, at least for recorded history, we know that as far back as 3000 BC, the Egyptians were playing games of chance. Don't know how much of the mathematics they were working out, but you can imagine they probably were interested in thinking about how likely they were going to win. Games aren't no fun if you think you're going to lose every time. So they were probably trying to figure out, should I play? Is it worth it? But now we're going to learn a little bit about how some of those numbers come up, whether it's a game or a rainstorm or whatever. Okay, something I want you to do. You thought, oh, she's doing this online. I don't have to actually do classwork. But you are wrong. Before you go any further, grab a coin. And it could be a penny, nickel, dime, quarter, whatever. Pause this presentation, and I want you to do what's called an experiment. You've heard that word before, probably in science class. It's a controlled operation that yields a set of results. So your experiment, your controlled operation, is to flip your coin a total of 50 times. But keep track of how often the coin lands on heads. Only flip it 50 times, but keep track for the first 10 flips, how many heads do you have? Once you get to 20 flips, how many heads do you have at that point? And when you get to 30 flips, how many heads total do you have at that point? When you get to 40 flips, how many heads total do you have at that point? And then finally, when you get to 50 flips, how many heads total? So you're keeping a running total, but like writing it down when you get to your 10, your 20, your 30, or 40, or 50. So let's say you had 3 heads when you hit 10. Then let's say you had 5 more heads when you hit 20. You'd have 3 plus 5 or 8. You know, write down the 8. You know, keep a running total at 10, 20, 30, 40, and 50. So as you're flipping the coin, your possible outcomes are heads and tails. You know, typical coin heads, usually there's a bust, a head of a person. And tails are something else, like an eagle or the Lincoln Memorial or something else. But you're interested in the event of flipping a head. So you're recording those numbers of heads and then keeping your data. So do that and then come back. Okay, so now that you flipped your coin, recorded your data, now take your data and make some fractions. For the first 10 flips, put your heads over 10. Once you hit 20, put your total heads at that point over 20. Do that for 30, 40, and 50. And in doing so, you have now given the empirical probabilities of getting heads on the next coin toss. So let's say at 10 flips, you had 3 heads. You have a 3/10 probability of getting heads on the next flip, on the 11th flip. Let's say you have 11 heads out of 20 when you hit 20. On the next coin, on the 21st flip, you have 11/20ths probability of getting a head again. That's what you're doing. You're actually figuring out what the probabilities or the chances are of getting a head on the next flip once you hit 20, 10, 20, 30, 40, or 50. If it was a perfect world, you're going to get heads, you know, 1 time for every 2 tosses. But we don't live in a perfect world, so it's interesting to look at these numbers. So pause this presentation, do those numbers, and then come back. All right, so you're back. How close were your numbers to 1/2? Because in a perfect world, it should have always been a probability of 1/2. One way of getting head out of 2 outcomes. But it's not a perfect world, so it's interesting, though, to look at your numbers. They shouldn't have deviated too far from 1/2 all the way through. If they did, then there might have been something wrong with your experiment as far as how the coin was flipped or how it landed or something like that. Or maybe the coin's got some kind of defect. Ideally, too, when doing an experiment like this, you probably set up a machine and make sure that it flipped the coin the same way every time. You'd probably also make extra sure that your coin was perfectly balanced and everything. But we're not worrying about that. It's just some demonstration. Alright, so yeah, in the real world, this is the kind of thing they do. Do experiment, take observations, and use those observations to establish probabilities. And again, the weather person, that's what they're doing. They're observing what happened with the weather in the past during those conditions and seeing, well, what % of the time did we get this outcome, like rain or snow or sleet or whatever. And then they're saying, well, on the next time that we have those conditions, that's the empirical probability that we'll have that outcome again, that weather outcome. We're in Florida, so I'm sure you've tracked hurricanes. We had some hurricane threats not too long ago. And when you're watching, we have one out in the Atlantic, but it looks like it's going to curve and go up before it ever hits a country. It might hit Bermuda, but it's not going to hit us. Came from Africa, it's coming over. But as you're looking at the reports about where it's going next, they can't tell you exactly where it's going next because there's too many variables. But they do give you the cone of probability. They say, you know, it's highly likely that it will follow a path within this cone. But they can't tell you exactly which path it's going to choose, but they can tell you the probability based on past storms and looking at their models, their computer models. All right, back to the pennies. You know, as you look at your fractions, do you notice any patterns? And I had asked earlier, I guess, when I was saying, yeah, look at it, see if it's close to a half. And what do you think might happen if I asked you to toss the coin more times? 100 times, 500 times, 1,000 times, 1,000,000 times? What do you think would happen? Ideally, the more times you toss it, the closer and closer your probability should get to 1/2, or it might even hit 1/2 and stay there. And that's something called the law of large numbers. When you're trying to look at empirical probability and make statements about the probability of something happening, you really should be basing your numbers on a large number of trials. Because the more data you can collect, the more accurately you can predict what's going to happen. It's like the weather. If they just started collecting weather data last week, do you really think that weather predictions would be very helpful? Probably not. But no, they've been collecting data for years, since the early 1900s. And the more data they collect, the better. I remember being a kid and dealing with hurricanes. They didn't have this cone of probability business back then. They hadn't developed their data collection and their mathematics as well back then. But now you've got the cone of probability, and who knows what will happen in the future. We'll never have perfect forecasting because there's too many variables, but you can imagine what might happen in the future with our models. And the coin flipping, yeah, the more you flip the coin, the better the prediction of what will happen on the next flip. Okay, so empirical probability, again, is what you were just finding. Number of times the event occurred, so the number of times you flipped heads, over total number of times the experiment has been performed. So total number of times you flipped the coin. Alright, let's do a quick homework problem, like from out of the book. Just dealing with the empirical probability. This particular problem, we're in 11.1. This particular problem is number 19 in the homework. It says, in a given week, a veterinarian treated the following animals. The vet treated 45 dogs, 40 cats, 15 birds, and 5 rabbits in that given week. Based on that, let's say another animal's about to come in the door. What's the probability that the next animal is a dog? Well, we're going to use the data collected from that week of animals treated and figure out what's the probability. Now, honestly, I don't think a week's long enough. I would personally want to look like over the year or over a couple of years to see the averages, or even like within the seasons over several years, because you probably have different animals, different seasons. But whatever, just it's a simplistic example here. All right, so empirical probability the next animal is a dog. Well, you have 45 dogs that had come in during the time period over how many animals? Let's see, 45 and 5 is 50, plus 40 is 90, plus 15 is 105. So the empirical probability that the next animal is a dog is 45 over 105. But make sure you reduce the fraction. Let's see. I know 5 goes in evenly, but so does, well, 15 will go in evenly. 15 times 3 is 45. And 15 times 7 is 105. So the probability is 3/7 that the next animal is a dog. Probability can be a fraction, decimal, or percent. So your 3/7, you can write it as 3/7 if you would like, and that's pretty common. They'll just leave it as a fraction, but make sure you reduce your fractions. Or you can divide 3 by 7, and you get a long decimal, so we'll just round it to 4 places. So you get approximately 0.4286, which you could also write as 42.86%. So it doesn't really matter which way you write your probability. They all are basically saying the same thing. So it's up to you unless the directions say what to do. What's the probability that the next animal is a cat? We had, 40 cats that had come in out of 105 animals. So we'll use that data to try to predict. And let's see, 5 goes evenly into 40 and 105. So that reduces to 8 over 21. And then the probability the next animal is a rabbit is 5 over 105. 5 goes evenly into those, so that's 1 over 21. So there's your probabilities. So there you have it. Alright, so that's empirical probability for you. From here on out, though, we're going to start working with theoretical probability. So the first part of the lesson, you have empirical probability. Then we're going to switch gears and we're going to go to theoretical probability. We're going to assume that all outcomes are equally likely to occur in all of our problems. So you flip a coin, equally likely to get heads or tails. There's no unfairness, no weighted anything. And we're going to follow what would happen theoretically. Like if you flipped your coin infinite times, what should your probability be? You know, if you looked at infinite veterinarian's offices, what would be the probability of the next animal being a dog? The theoretical probability takes the number of outcomes favorable over the total number of possible outcomes. In this process, you need to become very familiar with the deck of cards because there's going to be a lot of questions referring to drawing cards from a standard deck. We're going to have aces low, so aces are going to represent ones. And notice standard deck, you have 4 suits. You have your clubs, your spades, your hearts, your diamonds. We have 1 through 10, ace through 10. Then we have our face cards of jack, queen, king. Often in card games that's 11, 12, 13, but don't worry too much about that. Just those are the face cards, jack, queen, king. 52 cards in the deck, 4 suits, 13 cards in each suit. Because you have ace through 10 plus the 3 face cards, jack, queen, king. Alright, so theoretical probability. Instead of doing an experiment and flipping a coin or rolling a die, we're going to look at what should happen in an ideal world. Flip a coin. What's the probability of getting heads? Well, there's 2 possible outcomes, heads or tails. So the total number of possible outcomes goes on the bottom. And then the outcome favorable here is a head. And there's only one way to get a head when you flip the coin. The probability of getting a head when you flip a coin is 1/2. Probability of getting tail is similar, because again, you flip a coin, 2 possible outcomes, one of them is a tail. And that's it. That's the only 2 possible outcomes, heads or tails. Notice that if you add probability of head plus probability of tail, heads and tails are the only 2 possible outcomes. If you add those together, notice that you get 1. And that's going to be true. If you add up the probabilities of all possible outcomes for an event, it's always going to add up to 1. Probability cannot go higher than 1. And probability of getting anything else besides your head or tail is 0, because it can't happen. Alright? Roll a die. We're working with these kind here. We're not going to worry about fancy gaming dice or anything. Just this kind of die right here. Roll a die. Probability of rolling a 2. Well, there's only one way to get 2 out of 6 possible outcomes. Probability of getting a 7 is 0, because there is no 7 on the die. Probability of getting a 1 or 2 or a 3 or a 4 or a 5 or a 6 is 6 out of 6 or 1. So you have 6 outcomes total possible plus, and then 6 favorable outcomes that goes on top. Alright, draw a card just from a standard deck. Probability of getting a jack. Doesn't say what kind, just a jack. There's 4 jacks out of 52 cards. There's 52 total cards you could pick from. 4 of those have the favorable outcome of being a jack. So it's 4 out of 52 or 1/13. 13 cards in a suit, one of them's a jack. Probability of getting a card that's red is 26 out of 52. There's 52 cards to pick from. 26 of those have the favorable outcome of being red, because you've got your hearts and your diamonds, and that makes up half of your deck. And 26 out of 52 reduces to 1/2. Half of your deck. Okay, so some of these important probability facts I've already touched on. Probability of something happening is 0 when that something can't occur. Probability is 1 when it must occur. Probability always falls from 0 to 1 somewhere. The lowest is 0, the highest is 1, or it's some proper fraction in between. And the probabilities of all the outcomes of an event will add up to 1 every time. So that, remember that probability of rolling a 7 was 0, because on that die you can't roll a 7. And the probability of rolling a 1 or 2 or even up to 6, that was 1, because when you roll your die, one of those outcomes is going to occur. All the other probabilities are between 0 and 1. Probability of head plus probability of tail when you flip a coin was 1/2 plus 1/2, which was 1. So these two had to deal with rolling a die, and this one has to do with the coin. Okay. More important facts. Probability of something happening plus probability of something not happening equals 1. In that statement, a little algebra, you can rewrite it and say probability of something not happening is 1 minus the probability of it happening, which can be very helpful in the near future with problems where figuring out what the probability of something not happening might be too difficult. It might be easier to find the probability of it happening than doing the subtraction. Just to kind of give you a heads up. So, like, let's say you draw a card from a deck. Probability that you draw a 2. Well, there's 4 2s out of 52 cards, or 1/13. Well, the probability of not getting a 2, well, there's 48 other cards that are not 2s out of 52. That reduces to 12/13. But notice the probability of 2 plus the probability of not 2 is 1/13 plus 12/13, which equals 13/13, or 1. Let's say you want to draw a card, find the probability that it's not a black jack. The probability that it is a black jack It's 2 out of 52. Because you've got, what, the Jack of Spades and the Jack of Clubs. Could be one of those two out of the 52 cards. So 1 minus 2 out of 52, or 52 over 52 minus 2 over 52, is 50 over 52. Which reduces to 25 over 26. 2 over 52 reduces to 1 over 26. So probability of not blackjack is 25 over 26. So that's another way of finding it, rather than trying to sit there and count, well, how many cards aren't blackjacks? Instead, it might be easier to count the blackjacks and get that probability and subtract from 1. Alright, well, practice, practice, play with probability, all kinds of problems, and then next time we'll hit something that you frequently hear, especially with contests, games, is what does it mean when the odds are in favor or odds are against? I tend to think of Hunger Games. May the odds ever be in your favor. Well, we're going to talk about mathematically what the odds are and how to find them. Alright, so look forward to joining you again soon.